So we can start, and thank you very much for coming this semester. We are very happy to see you all here, and we are happy that we are here and we are progressing. Now we have our symbol, and it's a duck, and it's quantum duck. And for today, now we are coming for the speakers. Today we are going to talk about 1D materials, how they differ from other types of materials like 2D and 3D, which we discussed last semester, and which cool stuff we can find there. And today's speaker is Thierry Giamarchi, the professor of University of Geneva here, and I'm pretty sure that you all know him quite well. But before that, we will have a 15 minutes warm-up talk given by Giacomo, and he will tell us about where we can actually find with the 1D materials and show that they are real and we can actually work with them. Thank you, and the floor is yours.
Thank you for the introduction, Anna. So yes, I will talk about 1D materials and where to find them. So there are three main questions which can arise from this. The first is, okay, what are 1D materials? What do we mean? We are living in a 3D world. So let's try to define what is a 1D material. The second W would be why should we study 1D material? Why should we care? And there are plenty of phenomena as possible, but I will let Thierry explain this to you later. And the first question is, okay, where should we look to find them? I mean, from particle physics to huge universe in our world, where should we find them and what can we do to get them? So first, what is a 1D material? So the idea is that we are living in a 3D world. And however, being in 3D objects doesn't mean that necessarily can move completely freely in the 3D directions. So we can use forces or potentials to constrain the movement of different objects or systems. And a simple and intuitive example is gravity. So you all know of Newton when he got his apple on his head and then formulated the theory of gravity. And you all know, if you feel the gravity, and even if we are 3D, moving along the Z direction, the right, is a bit harder than the others. I mean, you all agree, we are all constrained to be on the ground. I can jump a bit, but I will not be able to reach the ceiling as easy as I can just walk on this side. So this is what we mean by, okay, we can use forces. So gravity can restrain me from going in a certain direction. And okay, now this is more 2.5D. So let's try to go to 1D. So still classically for get an intuition. I have here two examples. The first one is if you take a river which would be enclosed by two walls of rock. If you look at the water, it can either move forward or backward. If it moves on the sides, it gets against the rock and cannot go past it. It lacks the energy to go above it and pass it. So that's another important concept, that if you would have enough energy, then you could go up and pass it. So if I was strong enough in my legs, I could jump and go freely in the third dimension. The other example of 1D classical system, and you all know it, you've been in one of those, I'm sure, the tram or trains, they are constrained by tracks to move forward or backward. Hopefully you don't move sideways with a train, because then you have another problem which is occurring now. Okay, but still this is classical, so this is quantum club. What does that mean for in quantum physics to be one dimension? So first, one thing which we might recap is that this Sears or Planck found about quantization, and in particular quantization of energy. This means that in the classical view, you can have all values of energy you want. It's a continuum. So if taking this stick here, can make it go up here and gains potential energy in a continuous way. However, in quantum, the energy levels are quantized. So a system can only have a discrete set of energy, which are separated by them, between them. And the idea is that the lowest of them is called the ground state, and all the others are called excited states. And there is there are some forbidden zones in between where no states can exist. And what we will be interested in is the lower part of the excited state, so just above the ground state, and not completely bananas in energy scale, but not the ground state. So now if you look at a simple model, the quantum harmonic oscillator, you all know the harmonic oscillator. So this is just the quantum version. You recognize here the kinetic energy term, so the momentum square divided by the mass. But that's not the important part which I want to talk about, it's the potential part. So yeah, here the standard 1/2 m omega square x square, just for the 3D reaction. And intuitively, again, if you move away from the center, you have to pay energy. And if the frequency omega is larger, you have to pay more energy to get away from the center. So it's harder to get away. Now, if we take all of these omegas the same value, what happens in the states which you are allowed to have is that you have a ground state, as always, and by symmetry of the problem, because there is no difference between the different axes, all the excited state will just be the same for all the 3 directions. Now, if we now change these frequencies, let's say omega y and omega z, we take them extremely larger than omega x. So intuitively, you will have an extremely steep potential for y and z direction. It will be way harder to move in those directions. What does this translate in terms of the excited state? And that's what will happen is this, that now we will have some low excited states where you can move where only the x direction is involved. And at some point you will get again the excited state of y and z direction, but that will arrive at a higher energy. So the important part is you have a part of energy where concretely all your movement will be in the x direction. All the change you can have is in one of the direction, not all of them. And if you can constrain your system to live only there, meaning by lowering its energy, one example is that you have to lower temperature of a system to constrain it to stay in the low energy to limit its excitations. You can then have a system which lives only in 1D, or evolves dynamically only in 1 dimension, even if it's a 3D system at its core. Okay, so this is what I mean by 1D systems, and I will now try to speak out where you can find them. So there are 2 main subcategories of classes where you can find them. One is condensed matter. So here it is that you are playing with electrons, and you are studying the properties of electrons and how they move. And one example where you can find 1D system is what's called carbon nanotubes. So here you have a structure where each sphere here is a carbon atom. And as you can see, it's only a few atoms large in 2 directions. So let's say maybe 5 to 10 nanometers. And on the other hand, the other direction is quite long. I think maybe the longest is some alpha meter long. So 5 nanometers versus alpha meter, there is a bit of difference in how freely you can move in one direction or the other. Another possibility, still in condensed matter, is quantum wires. Here, the idea is that you can build this structure with semiconductor and insulators. I will not go in the complete details, just to give you a grasp of it. But what happens is that there is a plane where the electrons which we are studying will live. And by putting voltage via gates on top of below, you can put forces in this plane and constrain electrons moving only where you want them to move. And you can also then constrain them moving only in one in a 1D wire, hence the name. There are other realizations which exist, but I will now want to go to the other part, which is cold atoms systems. So now it's a completely other playground, where the main protagonists are atoms instead of electrons. And what people do is that they can use lasers, so they make opposing lasers to make standing waves. And now you will see as standing waves, you have as minima and maxima. And the atoms feel a potential by being with standing waves. And they will want to be in the minima of the standing wave and see it as a kind of an harmonic top, as I was discussing before. And so now you have confined atoms, and you can also lower the temperature of this system. So what they managed via various techniques, which are all more ingenious the one than the other, they can get down to 10 nanokelvin for this system, which is low enough to observe 1D physics. But another part, which what do we gain by studying this cold atom system? One thing is that since they are making the tops themselves really by hand almost, they can control it quite well. So they can control the interaction between the atoms. They can also control the lattice. So since they control how I put the laser which tap the atoms, they can control in the geometry in which they put the laser. So they can get rectangular lattices, diagonal lattices, hexagonal, you name it, they can probably make it. And they can also control how easily can the atoms move from one lattice side to the other. So that gives you a lot of flexibility in what you can do. And it's also useful to realize in live some simple theory model which you would study to simplify condensed matter systems. So this is the field of quantum simulation, where you're trying to simulate a simple time model in a real experiment with atoms. Now, I think a bit about cold atoms. Let's have to say, okay, but 1D here, how do you do it? So what it is that with tiny waves to which makes this tap for the atoms, you can put different strengths on the different directions. So you can imagine having extremely strong potentials on again, y and z direction, so really confine your atoms in this direction, and you are quite gentle with the other directions. This means that then you get a series of tubes, 1D tubes of atoms, which do not speak between themselves, and that's a realization of 1D physics in this case. Another possibility is also that since they can put atoms on lattice, this is a 2D image, actually a 2D snapshot of a system, and each blue dot which you can see is an atom. So what they can do is really say, okay, here I had an atom, here another one, and really count them. And they can put them on this 2D lattice, but the most important thing is that they can control how easily one atom can go from one horizontal line to the next one. So they can allow it to move, or they can put an extreme, again, strong potential, and confine it in only one line. So you will end up with a set of 1D chains, and again, you can get 1D physics out of this. Now, finally, here I talked to you about what they can do with this, but the how is quite complicated. And if you enter in one of these labs, what you see is this. So actually the chambers where the atoms are, in the end, are kind of, the chambers are this size, basically. And then the rest of the room is full of mirrors, laser generators, and a thing which I clearly do not understand enough, and quite complicated. And with this, I can conclude my talk, and I will leave you in the hands of Thierry for the next part.
May I briefly ask one question?
Sure.
So what is the advantage of cold atoms with respect to trapped ions? So one is charged and another is not, I guess, but you can make 1D line.
Yeah, okay. To realize 1D, don't have necessarily an advantage from one to the other. But as you said, ions are charged, while atoms are neutral. So that's allow you to have way more control on it. If you want to realize a Hubbard model, you want only your on-site interaction, not long range. Well, you would have long range interaction if you have charged particles, Coulomb. While if you have neutral, you won't have any long range, at least.
Okay, thanks. Are there other questions? Okay, then we can continue, and thank you very much. Yeah, Thierry, now the floor is yours. Do you need to reconnect something?
I just need, in principle, to open up the presentation. No? Ah, voilà. Should be able to close this. Close close that. Then, in principle, start the presentation, and you should see the same thing, and I should be able to hide the floating controls and perhaps put this at the bottom so it will not bother us. Okay, let's hope that everything is working. And before I start, I of course wanted to thank Giacomo for the wonderful introduction and presentation of the cold atoms and the 1D system. I wanted to thank the organizers of the Quantum Club. I think it's definitely quantum magic that make you so many at that ungodly hour to listen to a talk on quantum physics. So thank you all for being there. I see we even have very energetic and talented student right at the end of the amphitheater, and thanks to them for being there. Thanks to them for being there as well. So I'm supposed to tell you about quantum physics in one dimension, so I will not comment on all these logos that you see. I'm sure you know what they are, so I won't go in details. The only point I want to make is don't hesitate to ask any question at any moment. Don't wait till the end. I have slides to last me 2 hours, so don't hesitate to interrupt. It's not a marathon. We are going to go through a little tour of 1D physics, so it doesn't matter how far we go, but it's important that you enjoy the journey. So don't hesitate to interrupt and to ask questions. And now that's where, okay, I need to probably either click, normally it should work. Ah, yes, now it works. Okay, so I cannot resist, even if I will tell very little of what we actually do in the group, I cannot resist to show you an image of the group. And of course, if you want to know more, don't hesitate to go and have a look at the website. So we are entering the realm of quantum matter. I like this image by Zurek, who is one of the big player in the field of quantum physics. So we are stopping. We are stopping the classical world here and entering into the quantum world. And I really will start having problems, I guess, with okay. So what are the quantum properties of solids? So I will assume that you all suffered through more or less solid state physics 101 in one form or the others. You know that what we understand are free electrons, essentially, except that in real systems, the Coulomb interaction is of a very high energy. It's about an energy which is 10,000 Kelvin, which is comparable to the kinetic energy of the electrons. And so one could ask, what are the properties of real systems? In real material, can we really describe them by free electron? And there is a wonderful theory that was invented by Lev Landau, which in short tells, it's called the Landau Fermi liquid theory, which tells, yes, you can completely forget about interactions at the cost of replacing parameter like the mass of the electron by an effective mass. And that's the only place where the interactions will hide. And this was an incredibly successful theory because it gave the theorist the right to ignore the interaction, to deal with non-interacting particles, and therefore to use quantum mechanics of single particle to describe solids, to invent band structure theory, know why they are metals, they are insulators, they are semiconductors, give us the mastery of materials. And you know how materials are important for humans because they are all ages of humanity which have been named after one single material. You have the age of copper, you have the age of iron, and so on and so forth. So quantum mechanics gave us for solids the mastery of materials. And materials have played a central role. You're too young in the audience to even know what this drawing represents. It's a vacuum tube where you emit electron here by warming up. You have a grid which repel them or attract them depending on the voltage you put, and you collect them on the other side. So this is an amplifier. And thanks to this, people could build in 1947 the first computer. You can imagine the power that this thing was consuming. And here is a comment that was made in a journal called Popular Mechanics, which was a very good journal. And the person says, where a calculator like the ENIAC is equipped with 18,000 vacuum tubes and weight 30 tons, computer in the future may have only 1,000 tubes and weight only 1.5 tons. And you realize that despite the enthusiasm of the scientific news person, let's say the person got it completely wrong. And the reason why the person got it completely wrong is quantum mechanics. And these three gentlemen, Bardeen, Shockley, and Brattain, who invented the transistor. And thanks to the transistor, we are living in the society of information that we know today. If I had to name an age of humanity after a material, I would say 20th century is the silicium age, because clearly we are using transistor in practically everything we do. So clearly having the mastering of materials, and this was possible because of ignoring the interactions in the material science. Now, if I look at materials of the future, where we want to convert heat into electricity, magnetism into heat, electricity into magnetism, and so on, we have to make spin, charge, and orbital degrees of freedom of everything work together. And except playing dice with the periodic table of the elements, we need good theories to do this. And the message is we cannot ignore interactions anymore. So the game of ignoring interaction, it's over. It lasted 1 century. It was nice while it lasted, but that's finished. And so the materials of the future, we need to deal with 10 to the 23 particles which are interacting. Forget entangling 2 photons. 10 to the 23 particles, more than there are stars in the universe in 1 millimeter cube of material. So, and they are fermions. So, okay. So this is a challenging problem, let's say the least. Even if you try to put it on a computer, it's horrible. And it's even more horrible because the fermionic nature of the problem makes it that there are inherent numerical instability when you try to put such problems on a classical computer. This is why people are trying to invent quantum computers to overcome this thing. It's called the sign problem. Just to say that it's a difficult problem. So we are facing this problem, and that's one totally open direction in theoretical quantum physics and in material science. I will not solve it and show it to you a solution today, but I just want to point out that this is a real frontier of knowledge. You might have been used in saying, oh, I go to lower and lower dimensions, the infinitely small, you know what is in the quarks and whatever. This is knowing the basic laws of matter. That's a frontier of knowledge. Yes, that's correct. Going to galaxies, general relativity, black holes, gravitational waves, and so on. This is a frontier of knowledge. Yes, that's correct. But there is another axis that is as important, which is the axis of complexity. Even if you deal with particles for which you know very well the laws that control 2 particles, and we do. This is the Schrödinger equation, or this is the Dirac equation. There is nothing at the scale of this room that we don't know in terms of fundamental laws. When you put 10 to the 23 particles together, you get completely novel phenomena. More is different. This is a famous quote by a very famous physicist whose name is Phil Anderson. And so even if you have the laws for few bodies which are well known, it's completely a huge theoretical challenge to go to the case of many, many degrees of freedom, even for classical physics. And one good example of this is turbulence, for which people have a lot of problems solving classical equations. But when you put in addition quantum physics, this becomes a nightmare for theorists, or a paradise for theorists. Now, why less and less dimensions? I could give you the usual speech. You know, I could lie to you, say this is because future electronics involves more and more miniaturization. If you look at the number of transistors that have been integrated, over the year, you realize that the count is going over essentially numbers that I don't want even to write, 50 billions or something like this, which means the size of this object is shrinking. If you want to connect them, you need wires which will be tinier and tinier. You see the dimensions of the individual objects are going down, are sort of reduced to atomic dimensions. And so it's very natural to worry about objects in reduced dimensionality. But the real reason why you want to look in one-dimensional problem is because they are fun. And I will try to convince you during this talk that this is fun. And this is, for a theorist, I would say the main reason to look at this. I want to emphasize, and you might have heard for some of you about topological or edge states. I want to emphasize that one dimension is also important even if you deal with two-dimensional problems. So if I take this table, for example, and I put it under a very strong magnetic field, then what will happen is that the electron energy levels will be transformed into quantized Landau orbits, which I'm sure you all saw in your quantum mechanics course. But if you go close to the edge, the energy level are bended by the proximity of the edge. And so even if the bulk here is gapped, that you have filled the lowest Landau level, you see that the edge will intersect the energy level. So there will be objects that can propagate at the edge that are not gapped, and this will be 1D objects. So you will have at the edge of systems under magnetic field or under strong spin-orbit coupling, you have one-dimensional, sometimes people call them chiral states, which are propagating, and these objects are one-dimensional systems. So this is a huge branch of activity in solid states, which are called topological insulators, topological superconductors, and so on, and for which you have to worry about one-dimensional physics at the edge of these two-dimensional systems. So why is 1D special and why is 1D interesting? And Giacomo already gave you the key of that. Look, you live in 2D. Granted, you're not in 3D, you're in 2D. You cannot move away from the ground. But you have infinite interactions among yourselves. Not two of you can be at the same place at the same time. So in first approximation, we consider that you have infinite repulsion. Nevertheless, you can all behave as individual particles. One of you can stand up, go, leave the room, come in, and so on, just like if these interactions were not existing with the other people. And that's here what I summarized. You have one particle here. It repels the other, but it rearranges a little bit the density around, and then it can move practically as if it was alone. Maybe the mass is a little bit renormalized, but that's all. In a crowd, you know you can move. It's more complicated, but you can move. Now, imagine you're in 1D. You're queuing for the cafeteria, or you want to go to see a movie or whatever, and you're in a line. Or you're waiting for the tram, and there are 3 trams that follow each other. Why? Because if this object is repelling with this object, then it will push this one, which will push this one, which will push this one, and so on. So no individual motion is possible. The only thing that will be possible will be collective motion. So in 1D, everything is transformed from individual motion into collective motion. And that completely changes the nature of the physics. So you have a physics which is very different from the physics of individual particles. If you take a highway and you have only one lane, this car cannot behave as an individual car. It has to follow the global flow of the system. Okay. On a technical level, we are used very much usually to assume that there are certain types of order. The system becomes a superconductor or becomes an insulator or whatever, and then we do something called mean field theory on the top of it. Well, in 1D, there are a lot of fluctuations, and therefore all this method fails. So not only you lose the physics you know, but you lose most of the methods you love and you can apply in higher dimensions. So this is really a ground where you have to reinvent yourself because neither the physics nor the methods that you know are easy. So if I think about high dimensional systems, you know that there are well-defined statistics. You know that there are bosons which like to be with each other, and there are fermions who hate each other. And either you have bosons or you have fermions, and the bosons behave like bosons and the fermions behave like fermions. You have what I would call elementary excitations, which are relatively easy to identify. If I have a system, a solid in 3D, and I remove one particle, the least I can do is to remove one charge and one spin 1/2 at the same time. I remove one electron from the solid. I cannot do less than that. Cannot cut the electron in two and remove only the charge. I have to take at least a charge and a spin together. I can remove 2 charge and 2 spins and so on, but not less than that. So you can identify these elementary excitations. You have also typically well-defined trends. Either a material is a superconductor or it's an insulator or whatever. As we were discussing, you have well-defined single particle excitations. And I will try to show you on a couple of examples. I will not do any calculations and so on, but I want to show you on a couple of examples that all this is wrong in 1D. It doesn't work. So you have to replace it by something else. Okay. I will not do a calculation, so I will not be more explicit in step 2. A miracle will occur. I've put a couple of references that you will find on the video, so if you want to know. Warning, these are relatively advanced references, so it's not something, but you can find on YouTube a couple of lectures that I've given in various schools that you will maybe be a little bit more gentle than these references. And one thing that I would like to show is a little bit, maybe a take-home message, and also to show some of the faces of the heroes of the field, to show you a little bit by which method people attack the problem. So there was the old guard who did use standard Feynman diagrams, many-body theory, and so on and so forth. So Tomonaga, Luttinger, Gorkov, Dialoginsky, Larkin, the good Russian school, you know, you compute, you do 25 pages of so-called easy calculations. Good luck. There are people who invented methods. I told you, you lose the methods, but you can invent new methods. So there was one guy who invented a fantastic method, the person is Hans Bethe, who I'm sure you know for other reasons. He's the guy who understood how the stars are working, essentially. But he invented something which is called the Bethe-Ansatz. He guessed the solution. So there are models that can be solved by this method, which is called the Bethe-Ansatz. And this is a big, big field in mathematical physics. Because of course, which model are solvable, which model are not solvable, what is the solution, and so on. And the heroes are Hans Bethe and a physical mathematician in Princeton whose name is Elliott Lieb, who did a lot of things in this field. There is the standard field theories, which either you know or you don't have to worry about it. But if you do a master, you usually have a course on field theory or equivalent. And there are a couple of heroes, someone named Alan Luther, the late Vic Emery, and someone you know for another reason, whose name is Duncan Haldane, who got the Nobel Prize not so long ago, not for what I'm telling you, but for something connected, which is the topological aspect of matter. And finally, we have numerics with someone named Steve White, who invented a fantastic method which is called density matrix renormalization group, and people who elevated it to New Horizon, Uli Scholvöck in Mu. And the take-home message, which is the most important, is not so much that there are these methods, is that the reason why we are so efficient in solving 1D quantum problem and why maybe people are less efficient solving 2D quantum problem is that we learn how to make these 3 methods work together. So not a single of these methods can solve everything, but if you manage to have them all work together, then you get a weapon which is absolutely impossible to find. Because numerics is valid at short distance, short time, field theory is valid as long distance, long times, and so on. So you can go from one to the other and use the best method when you need it. So I would say that's certainly one of the take-home message of this lecture. Okay, so let me now start and go to one-dimensional quantum systems. Here are a couple of examples of systems, mostly in condensed matter. I'll show you cold atoms a little bit later. Organic superconductors, so-called Beshgard salts, which are made of stacked up molecules. So the motion of the electrons is mostly perpendicular to the screen. Very difficult for the electrons to go from one stack to the next one. So although the material is 3D, the electronic band structure is essentially 1D. The carbon nanotubes that you saw already in Giacomo's talk, so-called spin ladders, which are insulators, but each one of the blue sides carries a spin 1/2. So at the end, it's a quantum magnet, where each side here carries a little spin 1/2, which has magnetic interactions, well, at least something that looks like a magnetic interaction with the neighbors. The quantum wires that you already saw in Giacomo's talk, another quantum magnet, and the edge states in quantum Hall or spin Hall effect. Okay. Now, again, what is a 1D system? So just to push, it's a system where, because of quantization, typically in the transverse degrees of freedom, the quantum numbers that correspond to creating excitation transversely to the direction, let's call it X, is costing you a lot of energy. And because of quantum mechanics, we can get 1D systems, even if the size of the physical object is much smaller than the size of the channel. You know, an atom is much smaller than the size of the tubes that Giacomo showed you, but because the wave function of the atom is quantized, going from the quantum number n equals 0 to n equals 1 costs too much energy, so you only access the excited state, which consists in changing the momentum along the chain. So as long as your temperature, your interaction, your whatever only excites things here, you can completely ignore this, and it's just like only the quantum number in this direction are important. So that's a perfect theoretical 1D system. It doesn't mean that the wave function of the object is 0 dimension, but it means nothing changes in the perpendicular direction. And that's the thing which is important to understand. So let me show you a typical problem. Let's take bosons, it doesn't matter. I study an energy, p squared over 2m. Remember, gradient of the wave function in Schrödinger equation is the momentum. So this is just the kinetic energy of my bosons, p squared over 2m. Then my three bosons. Then I put an interaction. Two bosons see each other with a potential V. Usually we take a delta function here, just a contact interaction, and then a chemical potential, which tells you how many bosons you can put in your problem. This model is known as the Lieb linear model. Remember Lieb? He was one of the heroes on the first page. And that's a model that is exactly solvable by Behrens. As Giacomo was saying, on a model like this, you can add a periodic lattice if you want, made of light. So you send a laser here or you send a laser there, you create a stationary wave, and then the bosons could live in a periodic lattice, and so on and so forth. I will not go in detail. For people who are familiar with the technique known as second quantization, here is the same model, essentially written in a second quantized form on the lattice, directly on the lattice. It's the so-called Hubbard model, and because it's for bosons, sometimes people call it the Bose-Hubbard model to distinguish it from the fermionic equivalent. Well, these are kinetic energy in a tight binding representation and a contact interaction where two particles see each other if they are on the same side. Okay. So the first effect that I would like to show you is the fact that in 1D, forget about defining your statistics as statistics. You cannot separate it from the interactions. Why? Because in 2D or 3D, you get two particles. You want to know if they are bosons or fermions. What do? You do this. They never see each other. And then you know if the wave function takes a plus sign or a minus sign. But in 1D, what will you do? you will do this. They see each other. So if they repel infinitely, I cannot exchange them. So how do I know if they are bosons or fermions? And let me show you that you can test this. So let me take a limit of where I have a system where I have bosons on the line. So there are bosons. The wave function is symmetric. And now I put an infinite repulsion between the bosons. I claim that this system will be equivalent to spinless fermions. Because the Pauli principle that says I cannot put two particles on the same site will produce the same effect than an infinite repulsion between the particles. So if I have fermions, the fermions are free unless they are on the same site where Pauli says, no, forbidden. Quantum mechanics, forbidden. If I have an infinite repulsion, which is a contact interaction, the bosons are free unless they are on the same site. And then it's forbidden. So, are there fermions or are there bosons? Sometimes people call about the fermionization of bosons. So this is called the Tonks gas, of the name of the person who worried about this problem the first. So again, so you have to be a little bit careful because I'm cheating you. Because the wave function of boson is still totally symmetric. The wave function of fermions is still totally anti-symmetric. So what I'm telling you cannot be true for the wave functions, but it's true for the square of the wave function. The amplitude of the wave function has to go to 0 when there is another particle. But it doesn't tell you the sign. So actually what happens is that the bosons will have a wave function which will do this every time there is another particle, while the fermions will have a wave function that will do this every time there is another particle. The sign will change. But for the square of the wave function, if I measure the density, I will not notice the difference. Can you test this? Oh, yes. So, okay, let me skip this, which has no importance. So here is an experiment that was done in the group of Dave Weiss in Pennsylvania. He created the tubes. You see the section of the tubes here, as Giacomo was saying, and he measured something, which I don't want to go in detail, as a function of the repulsion between the bosons. These are bosons. The red curve is the free fermion curve. And you see that when the repulsion becomes larger and larger, the points for the bosons, they slowly and nicely go towards the free fermion limit. This is the bosonic curve. So this is an experimental realization of this gas where the bosons have fermionized. If you don't believe me, here is another experiment done in the group of Immanuel Bloch, nothing to do with the Bloch wave function, where he also realizes tubes. He also put bosons in the tubes. He goes to the infinite repulsion, and then he measures the momentum distribution. What is the probability of finding particles with a given momentum k? And trust me on this, if you go through this theory of fermionization, what you should find is essentially 1 over square root of k. Now, this is a little bit more complicated because his experiment is in a parabolic trap, which makes that the tubes have different densities and so on. But the curve that you see here, the solid curves, are the theory of free fermions in the trap. And you see that it fits beautifully the experimental results that he has. So in 1D, no way to distinguish statistics from interactions. You have to take both of them together because this is what will happen. Another very funny property of 1D that I want to show you is called the fractionalization of excitations. I told you in 3D, you have minimal excitation. For example, imagine I have a bunch of spins, 1/2. What is the minimum excitation I can do? I can take a spin 1/2, 1, and I can flip it. The variation of spin is 1. 1/2 minus minus 1/2. And I cannot do less than that. Everything else I will do will be multiples of 1. I can flip 2 spins, or I can flip 3 spins, or 4 spins, or 5 spins. But I cannot flip less than 1 spin. Okay, let's look a little bit in 1D. So let me take an Hamiltonian here where the spin interact with an exchange interaction. And if you remember your quantum mechanics, this term contains here Sx plus Sy plus Sz, and I can write it S plus S minus. So this term will flip 2 neighboring spins. One will go up, the other will go down. Okay, so imagine I have here a system, and I should have drawn it in 3D, but I have a system in which I flip 1 spin. I have a variation of the total spin, which is 1. And if instead of doing it in real space, as I'm doing it here, I was doing it at a fixed momentum q, I would create an excitation that has an energy which is directly dependent on the momentum q. And this excitation has a name, it's called a magnon in 3D. And in solids, in 3D, you have a lot of people who study magnon. Okay, so I have a particle, if you want. A particle which is made of an S equal 1 excitation that will propagate as a particle, which means it has a well-defined relation between its momentum and its energy. Now let's do it in 1D. I flip my thing, I have my magnon, but then I will apply the Hamiltonian. So I will flip these 2 spins, and then I will flip these 2 spins, and then I will go a little bit faster and do it twice on the other side. And now my magnon has melted, it's not there anymore. And you notice that here I have a region where I have 2 spin 1/2 which are close by, but then everything seems normal. And then I have again something where I have 2 spin 1/2 which are close by. So my magnon has exploded into 2 excitations, which people call spinons. And these excitations, first, they are non-local, because they are not just living here. Notice that this string is now turned in the opposite direction than the initial system. So it's like if I had a particle that has splitted into 2 collective and non-local excitation, but each one has taken 1/2 of the original spin of the system. And that's normally impossible. I cannot split the magnon. But in 1D I can. So this is what people call the fractionalization of the excitation, because here I managed to do an excitation that has a charge, if you want, a spin, which is impossible, which is only half of the minimum excitation I should be able to cause. And the spin-on is a very weird excitation because it consists in taking the spin chain and then turning everything on the right in the wrong direction. So it's a highly non-local excitation. You cannot, of course, excite it with a local probe. So that's why you need to excite 2 of them at the same time and separate. And again, this is weird, but this is the rule in 1D. This is the norm in 1D. And this is also why in 1D, there are hidden topological order parameters, because if you measure the phase here and the phase at the other extremity, if you didn't flip everything on the right, the difference of phase is 0, 0. Here it's 0 and pi, because you've changed the sign. There is another consequence, which is very funny, is that now each one of my spin-on will carry part of the momentum of the original magnon. So I can split the momentum as I want. But if I split the momentum as I want, the energy of the magnon or whatever is now made of the sum of the energy of the 2 spinons, which depend on their momentum. So depending on how I will split, I will have different energies. So instead of having a well-defined relation between the original momentum and the energy, I've now a continuum of energies. So instead of having a curve, which would be some curve, here it doesn't matter what is the shape of the curve, I now have possibility to get all these energies when I create such an excitation. This has a name, it's called the Descloiseau and Pearson spectrum. And this is a direct consequence of the fractionalization of excitation. Can you measure it? Yes. Take a quantum magnet that I already showed you. So just to show you the structure of the 3D system, these ladders are piled up in this surrounding. The coupling between the ladders are so small that you can sort of neglect it. So although the material is 3D, the physics is the one of a 1D ladder, not a single chain, but a ladder. And then you look at this using a probe, which is able to measure the spin degrees of freedom inside the solid. And such a probe is neutron scattering. There is a possibility to use neutrons to do this. And this is an experiment that was done by our colleague Christian Ruegg before he became director of PSI, when he had time to do physics. And this is the experiment. You see that there is intensity everywhere here. The people plotted here the de Cloiseau-Pearson spectrum. And on the right is the theoretical curve. And you see the agreement is not too bad. So this is something where you see this fractionalization of excitation that occurs in 2D. Just to say, numerically, now we are able to compute the same curves. And here is a calculation that was done by Pierre Bouillot and Corinna Collat using this method that I mentioned, DMRG, invented by Steve White, where here is the spectrum, so the intensity of trying to create an excitation of frequency omega and momentum q. I don't want to go in detail, but just to show you that we get excellent agreement with the neutron scattering experiment. So it shows that we can compute this thing. Let me skip this one, which is not important. Let me show you that you can go further. Imagine that instead of having just spins, I have electrons. What happens if I remove one electron? If I remove one electron, I remove a charge and a spin here. And now I play the same game. I let my spin flips. And then I have a region here where no charge is missing, but I have my two spin down here. So I have a spin on here. And if I let the particle move, I will have a region where I will have no spin missing. Up, down, up, down, up, down, up. Nothing seems to disturb the environment, but I have a charge missing here. And people call this a holon for a hole, if you want. So the fractionalization of excitation for an electron means that you have now separated the spin and the charge degrees of freedom. So now you have excitations that carry charge but no spin, and excitations that carry spin but no charge. And this by removing one electron which carried a spin and a charge. And of course you can take all the scissors you want and you will not cut an electron in two. But in 1D you can. You can because you convert it to collective excitation. So can you check this? So I won't go in detail, but here are experiments that were done in quantum wires by the group of Amir Jacobi, then in Weizmann and now in Harvard. And they did tunneling between the wires, and they see a structure which indicates that there are two velocities that corresponds to objects which tunnel. And essentially, of course, if you have a spin-on and a holon, each one has its velocity, and you should see these two velocities as independent objects. The theory was done by Jaroslav Cherkovniak and Bertrand Reed. Cold atoms, they can help you for that. These are experiments that were done in the group of Randy Hewlett in Texas. And he's doing an excitation where he changes the charge of the system. And of course, what happens is that you will see, if you give a given momentum to the system, that you see a resonance at a frequency, which is the velocity times the momentum of the excitation you do. And therefore, this allows you to measure the velocity of charge excitations. And this is essentially what was done in this experiment, and we helped a little bit for the theory. And this is the dashed curve is the theoretical curve, and the dots are the experimental dots. And so you see that you measure the velocity of the holon, which made some news journals say ultra-cold atom confirm 50-year-old physics theory. I don't know if it should be taken as a compliment or as an insult, but okay, never mind. You can test directly for the spin-charge separation, and here are experiments that are done in the group of Immanuel Bloch, the same, where they have a chain of atoms, but they are able to then separate physically by applying a gradient of magnetic field, the spin down from the spin up. So you see, if I see an atom in the lower box, it means it has a spin down. If I see an atom in the upper box, it has a spin up. And if I see nothing in each one of the box, I have a hole. And you can test, you can see that what they have here is exactly the structure I showed you. Down, maybe a hole, up, down, up, down, up, down, up, a hole, down. You start again with a down, up, down, up, down, up, down. And they can check that indeed you get the spin charge separation. So that this works as predicted by the theory. Meanwhile, the same Randy Hewlett managed not only to measure the charge excitation, but to measure also the velocity of spin excitation in the same experiment, and was also able to see this spin charge separation. So this is a remarkable. Let me finish maybe by showing you, after all, you could tell me, but what is wrong with this picture if I am in 3D or in 2D? Why don't I have spin-ons and hole-ons going, you know, each one in its own direction? Well, let's try it. I remove a particle, and I'll do the same thing. I'll flip the spins here. Notice what happens. The spins are flipping, but then I have these ones which are in the wrong direction compared to the neighbors. So this cost me a lot of energy. Now, if I do it here, I will have exactly the same thing. These spins are in the wrong direction compared to the neighbors. So now what I have is an energy string who's growing as the separation between the spin-on and the hole-on is growing. So it's like if I attach these two excitations by a spring, and they are confined. They are confined and they give you a particle, which is the electron. So if they are neighbors, if they are neighboring chains, the deconfinement mechanism between the spin-on and the hole-on doesn't take place. And the two particles are back to the original excitation. You can test this. I show you here something that is the spectrum in the spin chain for the confinement of the two spin-ons, because the same mechanism occurs. I have a string which is growing linearly with a distance between two spin-ons. You can solve it. It's like the hydrogen atom. They are bound states, except it's not a 1/r potential, but it's a linearly growing potential. I recommend the exercise in quantum mechanics. What is the hydrogen atom whose potential is growing linearly? What are the bound states and so on? You can do it. It involves Airy functions. It's beautiful. And here is what you should observe if you were doing neutron scattering. You see the resonance here. Every time you hit a frequency which is corresponding to one of these bound states between the two spin-ons. Here is the calculation. Here is the observation by neutron scattering experiments. So you see very well the bound state of the two spin-ons, and you see the confinement mechanism which prevent the spin charge separation. Let me skip the mode transition. I think my time is essentially up, so I'll skip this part. And I just wanted to sort of finish by not sort of going in detail, but just flashing a couple of hot topics where we are all excited just at the moment. So I will not go in detail. It's more to show you images. But of course, if you have questions, don't hesitate to ask. So dimensional crossover, how do you go from 1D to 2D or 3D by coupling 1D units? And that's a very exciting question. We are sweating on it. Lorenzo Pizzino and Epeng Yao are heavily working on this. We put a system which is 2D, and then we put a periodic potential which splits the system into tubes. So this gives very interesting and complicated phase diagram. And we could even discover that when we do this, you compress the system, and you all know what happens when you compress something. You all played with a velo pump. No, it cools. That's what we found. In 1D, because of quantum effects, it cools. So you compress the system and it cools. Funny, huh? That's called quantum mechanics. Okay. What happens in this organic when the chains are coupled? Well, it goes to a very complicated phase diagram when the electrons realize they can jump from one chain to the next after all. They are not obliged to stay in a single chain, and we absolutely don't understand the physics of this thing. You can do transport. This is something that they played a lot in the group of Tillman and Slinger. You make a reservoir of fermions on this side, you make a reservoir on fermions on this side, and then you send the particle through a 1D structure where you can create the periodic lattice of a solid by using lasers. And that's very beautiful experiments that allow you to do things. You can study Hall effect. You can study Hall effect with cold atoms, and you all know Hall effect. You know that it gives very simple answer in the classical limit. Well, when you put interactions or quantum mechanics, it gives you a Nobel Prize. Half of the Nobel Prize of Thouless was for the topological formula giving the Hall effect for quantum systems, which is known as the Thouless-Komoto formula. And with interaction, it's an open question. So we play with our colleagues in experiments who, with cold atoms, manage to do a Hall effect. You can put disorder. The disorder in 1D is fantastic. An exercise for all of you: solve the Schrödinger equation in 1D in a random potential. Okay, you're a little bit too late because Anderson did it before you. But if you do it, you'll get a Nobel Prize because you'll find something extraordinary. Even the weakest potential changes the nature of the wave function. Instead of being plane waves, they become exponentially localized. It's called Anderson localization. It's not diffusion. Normally you expect diffusion, and since Einstein we all know and love diffusion. But you get a very weak disorder. Normally the disorder should be too weak to do something, and it localizes. It makes the wave function decay exponentially. Just to show you the paper who did that, 1958. So that's what I mean when I say you're a little bit late if you want to do the same calculation. But there are a lot of questions. And I like the sentence of Anderson, which says very few believe the localization at the time, and further, so it's important. It's a very hot topic at the moment, and it has yet to receive adequate mathematical treatment, and one had to resort to the indignity of numerical simulation to settle even the simplest question about it. Well, we still have to resort to the indignity of numerical simulations, but to put interactions on the top of it. And so Anderson localization plus interactions is really a hot topic. They can be experimented in cold atoms. I won't discuss them. Here is the phase diagram as a function of disorder and interaction of bosons in a random environment. You can do out of equilibrium. Do you like horse race? You can do quantum horse race. You take particles, you all align them here. They're all moving on a 1D line here. Each one has its line. There is a bath that you don't see. There are plenty of other particles you don't see. And then you give the signal to start, and they all start.